Okay, so it's 12:31. We'll get started. Welcome, everybody. My name is Janine Barr, and I am a Senior Research Specialist with the New Jersey Climate Change Resource Center. I'll be your moderator for today's Climate Academy, focusing on our recently released report entitled New Jersey's Rising Seas and Changing Coastal Storms, report of the 2025 Science and Technical Advisory Panel. I am joined by the Resource Center's co-directors, Dr. Marjorie Kaplan and Lucas Markson, who will be assisting me in monitoring your chat and questions for our distinguished panelists. Today's webinar will last until 1:30 p.m. Other than today's presenters and our Rutgers team, you're all muted, so to communicate with us, please type your questions into the chat box. Please send your notes to panelists, as that ensures all of us working behind the scenes today will see your questions. We are recording today's webinar, and it will be available on the New Jersey Climate Change Resource Center website, which we will put into the chat now. We've allocated time at the end to get your questions, so please put them in the chat as we're going through the presentation. The 2025 STAP report and its companion summary and FAQ document can be found on our website, and Marjorie will put that into the chat as well. Thank you to our colleague, Dr. Oliver Stringham, for his help with today's webinar. So today we are very pleased to have Dr. Robert Kopp, Distinguished Professor in the Department of Earth and Planetary Sciences, who is the chair of the Science and Technical Advisory Panel on the sea level rise and changing coastal storms, and lead author of its report, who is also joined by Dr. Anthony Broccoli, who is a distinguished professor in the Department of Environmental Sciences and one of the panel members and report authors as well. On today's agenda, I will start us off with a brief introduction, then I'll hand the mic off to Dr. Kopp and Dr. Broccoli to share the sea level rise and coastal storm findings from the 2025 STAP report. They will wrap up the presentation with a brief overview of compound flooding and its impacts before we open the floor for questions. I also wanted to take a moment to acknowledge all the people who helped to make this report possible. You'll be learning more about each of these groups in a minute, but we wanted to flash their names on the screen and thanks for their time and expertise up front. Now for the introduction. Human-caused climate change is accelerating sea level rise in New Jersey. These rising sea levels and changes in coastal storm characteristics are rapidly increasing flood hazards along the New Jersey coast and in communities near tidal rivers, marshes, and wetlands. The STAP's purpose, or charge, which is the acronym for the Science and Technical Advisory Panel, was to identify and summarize the most current science on sea level change and changing coastal storms. The 2025 STAP report represents the findings of the third New Jersey STAP on sea level rise and coastal storms, to provide decision makers with the information they need to make informed decisions. As with previous STAP reports, this report aims to be policy relevant, not policy prescriptive. The report does not make recommendations about how decision makers should use projections. Such selections depend on value judgments, such as the level of risk decision makers and impacted communities are willing to accept when planning their long-term resilience goals, as well as how decision makers in impacted communities choose to trade off the near-term costs of risk reduction and the long-term sea level rise risk. As mentioned, there were two previous STAP reports. In 2016, Rutgers University researchers convened a panel of scientists to assess projections of future sea level and storm changes affecting the Garden State. To ensure the usability of their assessment, the scientists also consulted with practitioners to discuss how they would integrate the science into their decisions to enhance the coastal resilience of New Jersey's people, places, and assets. In 2019, the New Jersey Department of Environmental Protection, or DEP, engaged scientists at Rutgers to conduct new consultations with panels of scientists and practitioners to update its 2016 work to reflect the most recent climate science. NJDEP again engaged Rutgers to update its 2019 work to reflect the most recent climate science. Previous STAPs have recommended their estimates be reviewed and updated regularly and not to exceed every 5 years, and after the publication of relevant global or national assessments like the IPCC. These recommendations were the trigger for this 2025 report, which began its drafting process in 2024. This slide presents the steps involved in creating the 2025 STAP report. In the fall of 2024, we began our data collection stage, which included a call for literature and data, specifically published papers, accepted manuscripts, and associated data sets. We reached out to 144 scientists with expertise in the field and received over 95 submissions. This was also the time when sea level rise modeling was done by Dr. Pareen Kumar, which Dr. Kopp will discuss in a few slides. In December of 2024, the STAP gathered to discuss the most updated science and began drafting the 2025 STAP report. Once a complete draft of the 2025 STAP report was created, the draft was shared with other experts outside of the STAP for their review and input. We had reviewers and a science review editor reviewing the draft report for completeness and robustness. We also had a practitioner panel and a practitioner review editor who reviewed the draft report to ensure the findings of the 2025 STAP report were understandable. The review editors held the STAP accountable for making changes to improve the 2025 STAP report. After those changes were made, the report was published earlier this month. And just to emphasize the range of experts and the established procedures that were followed to publish this STAP report, the review of the updated science was done consistent with the National Academy of Sciences, Engineering, and Medicine's guidelines for report review, which you can find following the link that Marjorie will put in the chat. And our practitioners provided input through facilitated discussions and interactive activities during an in-person meeting to ensure the inputs of all practitioners were captured. And you can see one of these interactive activities in the photo on the slide. While the reviewers provided input on the STAP report, the practitioners provided input on the STAP report and that summary and FAQ document. And with that, I'd like to turn to Professor Kopp, who will continue with our overview of the STAP findings.
Thank you, Janine. So next slide, please. So we looked at sea level change in New Jersey's past and New Jersey's future. The first finding is that sea level rise is indeed accelerating both globally and in New Jersey. Based on geological data, much of it collected at Rutgers and Rowan universities, over the Common Era prior to the late 19th century, sea level in New Jersey rose at a rate of about ½ inch per decade. This is due to the regional effect of the land adjusting to the fact that there was a giant ice sheet to our north, in North Jersey and further north, during the last ice age. Over this time period, before the industrial era, global mean sea level change was minimal. Rates of sea level rise in New Jersey and globally began to exceed the pre-industrial values in the late 19th century. Next slide, please. From 1912 to 2021, sea level in New Jersey rose at about 1.7 inches per decade. Compare that to the ½ an inch per decade in the pre-industrial period, as measured at the Atlantic City tide gauge, the data from which are shown in the yellow curve in the top left. And that compares to an average rate of global mean sea level rise of about 0.6 inches per decade, shown in the gray curve on the left. The bottom panel on the left shows the rates of sea level rise as opposed to the level. If we look over the last half century, sea level rose at roughly 2 inches per decade along the Jersey Shore, compared to roughly 1 inch per decade in the global average. So about a 1 inch per decade difference. Next slide, please. If we look at the causes of sea level change, this pie chart is looking at the 5.5 inches total of sea level rise in Atlantic City from 1993 to 2021. About a quarter of that, 1.5 inches, is due to is due to the effects of that adjustment of the land to the end of the ice age. Another quarter is due to the global mean thermal expansion. That's the ocean expanding in volume as it warms up on global average. And about slightly less than a quarter, about 1.3 inches, is due to the melting of ice on land in Antarctica, in Greenland, and in mountain glaciers. The remaining quarter is due to a mixture of land water changes. That's the pumping of groundwater on average around the world and letting it flow into the ocean, to changes in atmospheric winds and currents. That's the ocean atmospheric dynamics term. And to the sinking of land, the subsidence that's caused by human activities, mostly local pumping of groundwater. Next slide, please. And this rise in sea level has had a substantial impact on coastal flooding in New Jersey. This bar chart here shows you the number of coastal flood days per year. That's the number of days per year in which the highest water level exceeds water threshold for minor flooding defined by the National Oceanic and Atmospheric Administration. And what we can see is that the total number of New Jersey coastal flood days have increased in frequency and magnitude over time as a result of sea level rise. In the 1950s, Atlantic City experienced an average of less than one coastal flood day per year. By contrast, over 2007 to 2024, there were an average of 12 coastal flood days per year, with annual totals ranging between a low of 4 coastal flood days in 2007 and an all-time high of 23 coastal flood days in 2024. Next slide, please. So that's what we saw in the past. Looking to future changes, the Science and Technical Advisory Panel concluded that the sea level projections produced by the Intergovernmental Panel Climate Change 6 Assessment Report, of which I was a lead author, and much of the integration work for those projections was done here at Rutgers, actually accurately represents the state of the science and provides a solid foundation for the work of the STAP. The images on this slide are showing you figures from the NASA IPCC sea level projection tool, which took the 2021 projections of the IPCC and allows you to dive in anywhere in the world, including, as shown on the right here in New Jersey, to the projections of the IPCC. Next slide, please. So the IPCC projections were based on a framework, a computational framework developed here at Rutgers called the Frameworks for Assessing Changes to Sea Level, or FACS. So what FACS does is it links together computational modules representing different parts of the causal chain from emissions and population growth over on the left to sea level change on the right, which seems to be omitted from this slide. And so just to illustrate, starting from emissions, from projections of emissions, we produce projections of global mean temperature change and changes in the amount of heat stored in the ocean. And those changes are then fed into modules that represent changes in how the ocean expands in response to that stored heat and how winds and currents change in response to that. That's that stereodynamic sea level term. Those projections of temperature also feed into modules representing how mountain glaciers melt, representing how the Antarctic ice sheet and the Greenland ice sheet respond. And projections of population feed into projections of changes of groundwater withdrawal and construction of dams and impoundment of waters and dams around the world. The ice sheet changes, the glacier changes, and the land water storage are fed into a module that takes into account how the Earth's gravity field and the Earth's rotation and the shape of the Earth's crust responds to moving water and ice around, which means that when you, for instance, melt ice sheet, you actually get different sea level rise in different places. And on all these terms are fed into a box missing on the right, but those are the projections of global mean sea level and relative sea level change, where they are also augmented by projections of vertical land motion. So that's what the IPCC did. And one thing I wanted to draw your attention to, because it will come important later, is that when the IPCC and when the STAP produced projections of ice sheet changes, we used multiple alternative ways of doing that because the ice sheet changes in particular are on the frontier of scientific understanding. There are things that scientists don't understand very well about rapid ice sheet collapse or the processes that might lead to it, but that might have important implications for the sea level rise people are facing around the world. So when the IPCC produced its projections, in addition to projections for a suite of different emission scenarios, factoring into account processes that are relatively well understood about ice sheets, it also had some side cases that factored into account different ways of representing rapid loss of ice from Antarctica and Greenland. And the framework we use for the STAP is exactly the same as the IPCC framework, except for some computational updates that have occurred since the 2021 version, and a change that allows us to produce these so-called low confidence or potential rapid ice sheet loss projections, not just for a couple of emission scenarios, but for all of the emission scenarios we're looking at. So you'll see the implications of that in a moment. Next slide, please. So in the STAP, we looked at 4 different emission scenarios, focusing on 3 of them. And these are the same, or are part of the same set of emission scenarios that the IPCC used, called the shared socioeconomic pathways. So we have a look, and you can read the jargony numbers on the left if you want. I'm just going to refer to them by the labels. We have a low emission scenario that leads to a likely warming relative to pre-industrial of about 1.8 degrees Celsius, with a range of 1.3 to 2.4 degrees C at the end of the century. So this is a scenario that's most consistent with international climate goals, and it's comparable to what was called the low scenario in the 2019 STAP report. There is an intermediate emission scenario that is consistent with energy system modelers' projections of where current global policies are taking us, that has a central estimate of warming of about 2.7 degrees Celsius at the end of the century, with a range of about 2 to 3.5 degrees Celsius. And there is a high emission scenario, with about 3.6 degrees Celsius of warming, a range of about 2.8 to 4.6 degrees Celsius. That is comparable to what the 2019 STAP called the moderate scenario, because at the time of the 2019 STAP, projections of where current global policies were taking us was about 3.3 degrees Celsius. So notice that has come down in the period since then. And finally, for comparison to the 2019 STAP, we also include in the appendix a very high emission scenario, one with 4.4 degrees C of warming and a range of 3.3 to almost 6 degrees of scenario, which is comparable to the 2019 STAP's high scenario. Next slide, please. So this is the key table of the report, and there is a lot in here. So you will see, first of all, over on the leftmost columns, we are looking in the rows at numbers that have different likelihoods of being exceedance. So for instance, that first row of numbers, all of the different ways we have of calculating sea level change agree there is at least a 95% chance, at least a 19 and 20 cents chance that the actual number will be higher. And all these values are relative to the 1995 to 2014 average sea level, which is the same baseline used as the IPCC. The next row, there's an 83% chance of exceeding. The next row, about a 50% chance if we ignore the potential for those rapid ice loss processes. And the next row, there's a less than 17% chance of exceeding if, again, we don't consider the potential for rapid ice sheet loss processes that are of poorly known likelihood. The next 2 rows, we actually do try to take into account those potential rapid ice sheet loss processes. And so that next row, they even when you take those into account, we agree based on different modeling approaches that there's a less than 17% chance number, even accounting for potential rapid ice sheet losses, of exceeding that number. And then the last set, less than 5% chance, using IPCC terminology, where we would say it's extremely unlikely that that would be exceeded. And so we have these sets of numbers. The less than 95% chance, using colloquial IPCC language, is extremely likely to be exceeded. The white boxes, that is what IPCC would call the likely range, meaning there's at least a 2 in 3 chance the correct number is in that range, although again, that excludes potential rapid ice sheet losses. And then the next row extends the likely range by accounting for potential rapid ice sheet loss processes. And then the last set, extremely unlikely to be exceeded, as I said. Okay, so those are the rows. And then the columns, we have, first of all, at the highest level, we have across emission scenarios for 2040 and 2050. One of the findings is that sea level rise through the middle of the century is not very responsive to potential changes in emissions, because emission changes are relatively slow, and the oceans and ice sheets are relatively sluggish in responding to them. So through 2050, we don't care that much about emissions, but beyond 2050, we do. And so there you can see low, intermediate, and high emissions, broken down to 2070, 2100, and 2150. So just to point out a couple of key findings. So relative to 2005, the 1995 to 2014 average, it is likely that by 2050, we will see a sea level rise in New Jersey of between 0.9 and 1.7 feet. And if we're in an intermediate emissions scenario, it is likely by 2100 that we will see sea level rise between 2.2 and 3.8 feet if potential rapid ice sheet loss processes don't kick into effect. And even if they do, it is still the likely range will extend from 2.2 to 4.5 feet. And it will still be extremely unlikely that we would exceed 6.2 feet. By 2150, as you can see, the potential for quite large numbers shows up if those rapid ice sheet loss processes kick into effect. For instance, by 2150, accounting for potential rapid ice processes, the likely range on the intermediate mission stretches from 3 feet to 12 feet. Now, consistent with previous STAP report and these projections, we take Atlantic City, which has the longest tide gauge record in the state, has representatives, but projections for Sandy Hook and Cape May, which are other tide gauge locations, are similar. All of those sites are on the coastal plain. If you look a little inland onto bedrock, as for instance at the Battery in Manhattan or in Philadelphia, projections are modestly lower because that subsidence associated with groundwater withdrawal term we talked about doesn't come into play when you're not on the coastal plain. Next slide, please. Now, that's one way of looking at it, and there's a lot of numbers there. But the other thing to remember is that sea level is rising in New Jersey. It was rising before the industrial period. And so we will actually exceed different amounts of sea level rise in the future, and the uncertainty is actually in when. So this figure here on the right is sort of trying to visualize that. So under the low, intermediate, and high scenarios, that's what each of the rows within a panel, um, the different subparts are showing when 2 feet will be exceeded, when 3 feet exceeded, 4 feet, or 5 feet, and that the x-axis there, those are dates from about 2020 to 2300. So for instance, under a low emission scenario, New Jersey is likely, by which we mean at least a 66% chance in the absence of potential rapid ice sheet loss processes, to exceed 2 feet of sea level rise sometime between 2060 and 2125, and exceed 4 feet between 2120 and sometime after 2300. So that's the scenario consistent with international climate goals. Under an intermediate emission scenario consistent with current policy, New Jersey sea level rise is likely to exceed 2 feet between about 2055 and 2095, and to exceed 4 feet between about 2100 and 2195. Again, not including potential rapid ice sheet loss processes. Even accounting for the potential impact of potential rapid ice sheet loss processes and looking across all the emission scenarios, New Jersey sea level rise is extremely unlikely, less than a 5% chance to exceed 2 feet before 2045. In an intermediate emission scenario, extremely unlikely to exceed 4 feet before 2075 at the earliest. Next slide, please. So just as we looked at the historical changes in coastal flooding associated with sea level rise, there are future changes in coastal flooding associated with sea level rise, even without considering future changes to storm characteristics, which is what my colleague, Professor Broccoli, will talk about in a moment. Just from the fact that sea level is rising, future coastal flooding will be more frequent and more intense. So this table here is showing you for time from 2020 through 2150 for the minor coastal flood level. So that's the same flood level that was the minimum for the bar chart we looked at before. How many flood days per year we expect on average at Atlantic City. So in 2020, the likely range is 6 to 13 days per year on average. By 2050, that grows to 29 to 148 days per year. And by 2100 to 227 to 359 days per year. Even if we just pin our eyes on the extremely likely number, right, the most conservative projection, we see about a tripling of coastal flood days by 2050 and a nearly 25 or about 25-fold increase by 2100. So, right, so even modest amounts of sea level rise are driving this rapid increase in the frequency of coastal flood days. Next slide, please. And here I'm going to turn it over to Professor Broccoli.
Thank you very much, and good afternoon to everyone. So obviously, as you've just seen, sea level rise can produce more frequent flooding, even without any changes in coastal storms. But I'd like to talk a little bit about what our expectations are for future changes in those storms. So next slide, please. Here in New Jersey, we're affected by two different types of coastal storms. We have tropical cyclones. That's the generic term we use for tropical storms and hurricanes. These are rapidly rotating warm core low pressure systems that begin over the tropical oceans. They can produce very high wind speeds, as high as almost 200 miles an hour, and they vary in their size and intensity. Important thing to know about tropical cyclones is that they derive their energy from the warmth of the underlying ocean. We also are affected in New Jersey by extratropical cyclones. These are actually more common than tropical cyclones. We call them often nor'easters, and these are typically larger storms that form outside of the tropics. And as pictured in the illustration there on the far right of a nor'easter from a few Januaries back, these storms can affect large regions of the East Coast simultaneously. But an important difference is that they derive their energy from contrasts in temperature. And that's why the strongest extratropical cyclones tend to occur in the winter when there's a greater temperature contrast between the Arctic regions and lower latitudes. Next slide. So higher sea levels are raising the baseline for coastal flooding, which means that even without any changes in coastal storms, the flooding will be greater in the future. What the storms do through the action of their winds is push water from the ocean onto the shore, a phenomenon that we refer to as storm surge, and that exacerbates the flooding that might occur even without a storm. Next slide. In terms of tropical cyclones, we see that looking back since the 1980s, their frequency has increased over the North Atlantic region. Now, looking at storm frequency over time is a little bit of a complicated business because some of these storms spend their entire life cycles out over the ocean. And until we had widespread satellite surveillance of our oceans, we don't have a good handle on whether or not we were missing some of these storms. But we've had good satellite coverage since the 1970s, and that allows us to say that they have increased in frequency since the 1980s, and I'll show you a graphic on that in a minute. The overall intensity of tropical cyclones in the Atlantic and the rate at which they intensify have both also increased in recent decades. Now, what complicates matters is when we try to explain why this has happened, because there are a number of potential drivers of these changes that could be responsible. We have the increases in greenhouse gases, which warm the earth, and with tropical cyclones deriving their energy from the warmth of the underlying ocean, that potentially can contribute to stronger storms. We have decreases in particulate matter pollution, which can reflect sunlight back to space and counteract some of the effects of greenhouse gases. And there's also natural variability, and natural variability can be very important for storms like this, which occur relatively infrequently. You know, maybe a typical season is about a dozen or a little bit more storms. And so seeing changes over time is also potentially an effect of natural variability. Now, because the Earth is warming and a warmer atmosphere can contain more water vapor, the historic rainfall intensity of tropical cyclones is also increasing with climate change. Now, will the number of these storms increase? Based on what we know at present, the average annual number of hurricanes is not expected to change in the future, although we do expect the trends in storm intensity in terms of wind speed and also rainfall, and the rate at which these storms intensify to increase with greater warming. And I'm going to show you some evidence for what has happened so far. Next slide, please. What is shown on this graph is the trend over time in the ratio of North Atlantic major hurricanes to all hurricanes. So basically, it's telling us what fraction of hurricanes become major hurricanes, category 3, 4, and 5 storms. When we get back before the 1970s, you'll see that there's two lines. There's a bold line and a dashed line. The dashed line is what was actually observed. But remember what I said before, until satellites went up, the only way we would see storms that only affected the ocean is if there happened to be ships that were unfortunate enough to be passing within their vicinity. So the bold line here is an effort to adjust for that lack of global coverage that we have since satellites began. That means we have to adjust the frequency of storms upward from that earlier period before we had satellites. When we look at it from this perspective, we see that there have been large interdecadal changes in the number of storms. But since 1980, that number has been increasing, or more properly, the ratio of major hurricanes to the total number of hurricanes. So hurricanes over the last several decades have become more likely to reach major hurricane status. Next slide, please. Storms are also intensifying more rapidly. This graphic is based on some work by Andra Garner, in which she's looked at North Atlantic tropical cyclone intensification rates over 3 different periods. Early in the satellite era, labeled historical, the column on the left. More recently, the column on the right, and an intermediate period in the middle. And what we see for intensification over different windows of time is that there are more rapidly intensifying storms now than there were in the past, as many as 2 to 3 times as many storms in the modern period intensifying rapidly as we saw during the historical period. And the next slide will show you an example of one of these storms, a very recent example. Next slide, please. This is Hurricane Melissa, which happened just last month, hit the island of Jamaica as a Category 5 storm. In its rapid intensification over the Caribbean Sea, Melissa strengthened from a tropical storm to a Category 4 hurricane in just 18 hours. And rapid intensification is particularly dangerous because it gives people who are in harm's way less of an opportunity to know that an intense and maybe even extremely intense storm is coming. Next slide. Now, hurricanes get a lot of attention. We give them names. They're covered very thoroughly in the media. But as I mentioned earlier, extratropical cyclones, nor'easters, are far more common in New Jersey, and they can be impactful as well. Just a couple of pictures here to illustrate that. One going back a few decades to a big nor'easter in December 1992. And what you're seeing is storm surge pushing water up high enough to enter the Hoboken Path Station, and that water surging down the stairs and onto the tracks. This was a very impactful storm, closed the Garden State Parkway for a while, and had major impacts throughout the New York, New Jersey metropolitan area. But just last month, we had a nor'easter that rose water levels to basically equivalent to as high as they've been since Hurricane Sandy. And you see here some street flooding in the town of Manasquan on the Jersey Shore. These storms happen more often, And even though the most severe hurricanes may produce larger impacts, they can be very impactful as well. Next slide, please. Next slide. So, let's go back one. So in terms of our findings for extratropical cyclones, we know that the precipitation intensity of extratropical cyclones has been increasing over time. However, asking the question, are they becoming more frequent? Are they becoming more intense in terms of their winds and potential to drive storm surge? And are their tracks changing? All of those things remain an area of active research. And there is no definitive consensus regarding such changes now, although we hope that in the years to come, the research that's going on will shed more light on this topic. Similarly, predictions of long-term trends in extratropical cyclone changes are limited, and they are also an area of active research. Next slide. Both with tropical cyclones and extratropical cyclones, an issue that we sometimes have to deal with is that of compound flooding. This is an image of the Raritan River waterfront in New Brunswick in the aftermath of Hurricane Irene in 2011. At the same time that Hurricane Irene's winds were pushing storm surge inland, affecting the New Jersey coast and a lot of its bays and estuaries, it was also producing torrential rains over inland New Jersey. So at the same time that the storm's strong winds were pushing water up the Raritan River estuary, the heavy rains were pushing floodwaters down the Raritan River estuary. And this storm produced one of the highest water levels on record for the Raritan River. So when we think about future storms, we want to think about not only their impacts on storm surge, but also their impacts on rainfall. Next slide, please. So to finish, I want to remind you again that even though there is a lot more that we would like to know about how coastal storms will be changing in the future, higher sea levels are going to increase flooding and increase the impacts of these storms, regardless of whether or not there are any changes in the frequency and intensity of hurricanes and nor'easters. So now I'll turn it back over to Professor Kopp to talk a little bit about some of the impacts of sea level rise and coastal flooding.
Great. Thank you, Tony. So the report also concludes, as Tony said, by looking at some of the impacts of these projected and current changes. The next slide, please. In particular, we look at 4 different categories of impacts. One is coastal erosion. And we conclude that New Jersey's shorelines will continue to experience significant erosional pressure driven by storms and sea level rise, and that the resulting changes in the shoreline are going to be strongly influenced by local geomorphology and the extent of coastal engineering, which is among the most extensive in the country here in New Jersey. While current levels of intervention, that things like beach replenishment, have been successful at reducing erosion rates, those efforts may become economically unsustainable in the future in some areas, particularly for lower income communities. Next slide, please. Another impact is on coastal wetlands, and we may be at a critical threshold for some of our wetlands. Between 1993 and 2021, average sea level rise on the Jersey Shore was about 5 millimeters per year, or 2 inches per decade. This is near the maximum rate of sea level rise that coastal wetlands may be able to keep pace with simply by growing in response. There's a body of literature that suggests that there's a critical threshold that is around 7 millimeters per year. So many of our wetlands may be on the cusp of not being able to keep up with increases in the rates of sea level rise. Next slide, please. As the water level, the ocean level rises, sea level rise can cause saltwater intrusion into both groundwater and surface water. And barrier islands are expected to be particularly vulnerable, especially those that pump large volumes of groundwater. But though we can say something about the overall direction, there are a few studies that have examined the specific site-specific vulnerability to saltwater intrusion along the New Jersey coastal plain. And so we have low confidence in whether particular sites will experience saltwater intrusion over the next 50 years. Therefore, management of coastal water resource requires increased monitoring and modeling of saltwater intrusion. Next slide, please. And beyond the intrusion of salt, there's also the fact that rising sea levels interact with groundwaters in a way that increases groundwater-driven flooding. Again, there's high confidence that these rising sea levels and their interaction with groundwater will lead to more groundwater flooding. That's basically flooding that comes from below. But there's not modeling that allows us to say substantially which communities will be most impacted. So this is another important area of investigation. Next slide. So in summary, addressing the impacts of coastal climate change requires an integrative and adaptive approach that considers dynamic feedbacks among these different types of impacts. There's flooding, erosion, effects on wetlands, and effects on groundwater and surface water supplies. Human activities, including beach nourishment, shoreline stabilization with hard structures, dredging, and coastal development, further modify these processes, sometimes amplifying vulnerabilities by constraining natural adaptation pathways. Think about the fact that, well, in some cases, coastal wetlands respond to sea level rise by growing up and moving backwards. But if you have a road preventing that migration, they can't do that. The future resilience of New Jersey's coastal environments will be shaped by how effectively planning and management approaches integrate process-based understanding, account for nature-based strategies, and consider the differing capacities of communities to adapt. Next slide. Thank you.
Thank you so much, Dr. Cobb and Dr. Broccoli. Now I will take a look to Marjorie, who's been following the questions in the chat to kick off our Q&A.
Great, and Lucas is helping me, so if other folks are putting questions in, go ahead. Thank you so much, Dr. Kopp and Dr. Broccoli. I am going to start with a couple questions by John Hurdle. One has to do with whether or not, if current global emissions are sustained, how much sea level rise do you expect in New Jersey by 2100?
Yeah, so current emissions, that would be consistent with our intermediate emission scenario. That's a projection of current policy, which actually does have a little bit of a decline, but more or less different approaches get you to around 2.7 degrees C median projection of warming by the end of the century. And so under that intermediate scenario, we project a likely rise of 2.2 to 3.8 feet by 2100 if we don't see these rapid ice sheet loss processes kicking in. If they do, then that extends the likely range up to 4.5 feet. And it is possible, although extremely unlikely, that you could see sea level rise by 2100 as high as about 6.2 feet under that scenario. So the central range there would be either 2.2 to 3.8 feet or 2.2 to 4.5 feet, depending on how you consider the likelihood of ice sheet instability.
Great, thank you. And another question from John is, are other U.S. Atlantic coastal states also subject to land sinking?
Yeah, so again, in New Jersey, we have two major drivers. One is what we call glacial isostatic adjustment. So that's the subsidence of the land that was driven by the fact that there was a giant ice sheet that effectively deformed the crust and mantle underneath it and pushed up the surrounding crust and mantle. And so up until New England, you see subsidence associated with glacial isostatic adjustment, and you see that further to the south, although sort of the mid-Atlantic region is a peak of that. And then we also have this factor of subsidence associated with groundwater withdrawal, and that's a phenomenon of the coastal plain. So the coastal plain, sort of starts in Long Island and New Jersey and continues south, and you certainly see subsidence around there. Norfolk has among the fastest rates of sea level rise in the country after the Western Gulf of Mexico.
Thank you. So we have a question from John Callahan. How was the number of annual flooding days computed from sea level rise projections? Did you follow the methods in the 2022 tech report, Phil Thompson's 2021 paper, or another method?
Yeah, so we used to approach similar to that Billy Sweet did in the 2022 tech report, but it's basically calculating the distribution of historic water levels and then shifting it based on sea level rise.
Great. I think this is a question for Dr. Broccoli. I think it's just a clarification for Bill Shadle. Just to clarify, I think he thinks or wrote, does TC frequency increase does not equal more TCs?
Yeah, so when we talk about an increase in frequency, we're talking about whether or not there are going to be more storms. And the best evidence we have right now is that we don't expect the total number of TCs to change very much going into the future. Now, this is still an area of active research, but that's what the evidence is suggesting right now.
Got it. Thank you. And for clarifying that. And we have a question. I think this is also for you, Dr. Broccoli. Do we know why there were so many fish storms this hurricane season? There seemed to be a shift to the east and an intensification of those storms. And I'm pretty certain you may want to clarify what is meant by fish storms, and you probably know what it is.
Yeah, I certainly do. Those of us who follow hurricanes and tropical storms will call a storm who remains out over the ocean throughout its path as a fish storm because it doesn't affect people, it just affects fish, or so the saying goes. And this year is an unusual one in that we had close to the average number of tropical cyclones in the Atlantic, but none of them made landfall in the United States. Of course, we did have landfall from Melissa in Jamaica and Cuba, but none making landfall in the United States. I can tell you why that happened, but it may not be a very satisfying answer. During the hurricane season, we've tended to have a low pressure trough in the upper atmosphere near the East Coast that was turning these storms away to the Northeast before they got close to the US coast. Hurricane Erin got relatively close, but still stayed a couple hundred miles offshore, even though it did produce some big impacts. What's unsatisfying about that explanation is I can't tell you why that trough was there, except that it is part of the normal variability of our atmosphere to have these ridges and troughs that steer the jet stream in different places from year to year. And that happened to be where it was this year.
Great. We have a question that I think also is probably one for you, Dr. Broccoli. Amir Beg Mohammadi asks, is there active research on tropical cyclone to extratropical transition under climate change? In particular, do we have evidence that the frequency or characteristics of these transition events are changing?
So the broad answer to that question is yes. There's a lot of people throughout the meteorological community who think about things like extratropical transition. One of the potential concerns about a warming climate is that storms may retain their tropical characteristics longer as they move out of the tropics because of not only changes in sea surface temperatures, but also potential changes in the upper level winds that are important in initiating that extratropical transition process. People are studying it. There are some indications from some papers that perhaps they will retain tropical characteristics at higher latitudes, but I think we still have more to learn about the details.
Great. Well, we do have a question from one of our former students, so I'm going to ask that from Johnny Quispy. Across the RCPs and scenario projections, has there been any significant or noteworthy changes across the scenarios that may have influenced sea level rise projections? If so, what's changed?
Yeah, Janine, if you could bring up slide 50. Okay. Thanks. Yeah, so this is a comparison of the projections from our 2019 report and the 2025 report. And the principal difference is in the set of scenarios we're considering, right? So in the 2019 report, we looked at a 2-degree scenario, a 5-degree scenario, and an intermediate scenario or moderate scenario that was 3.5 degrees at the end of the century. And that 3.5 degrees was consistent with what projections a decade ago said current policies were taking us towards. Current policy projections from Climate Action Tracker in 2016 put us around 3.5 degrees of warming at the end of the century. Because of both policy and the energy transformation, current policy projections put us with it towards a central estimate of warming around 2.7 degrees C, which is our new intermediate scenario. And the high scenario now has a warming level at the end of the century that's sort of consistent with the moderate scenario in the 2019 report. Now, interestingly, if you do an apples to apples comparison, the 5.1 foot number in the 2019 report included the potential rapid contributions from potential rapid ice sheet losses. So you can compare the same number in this report, which is that boxed on the right. The high scenario is 5.2 feet. So in the end, probably the things that make the biggest difference in the projections of the report are actually the fact that emissions projections have come down under current policies, so that our central scenario is around 2.7 degrees instead of 3.5 degrees C.
Got it. So I have a question here from Rachel Davis that I'm kind of reframing a little bit to make it quicker. How might your predictions change if taking into account recent approvals of more gas pipeline infrastructure in the Northeast?
Yeah, I don't think they would change. The effects of any single policy on global emissions is quite small. As I said, there was one analysis, it may have been from Rhodium or Climate Action Tracker, that basically suggested that the effect of U.S. policy changes in 2025 amounts to about 1/10 of a degree C warming at the end of the century. So when you go down to the level of individual infrastructure projects, you're really not talking about something that would have an impact on sea level rise. That doesn't mean they don't have costs. In another half of my life, I do a lot of work on something called the social cost of carbon, which is looking at the economic value of even ton level emissions of carbon dioxide. But in the sea level rise projections, this is small. Now, let's suppose that is actually part of a global cascade of changes that is not simply one pipeline here or there, but actually it's a reversion from where we are towards in a world where emissions growth is slowing and maybe even emissions are stabilizing to a world in which emissions are growing at a sustained rate. And speaking off the cuff, I would say things like renewed growth of U.S. emissions driven by data centers and the like actually might have more to do with that than individual infrastructure projects. But you can get a sense by comparing then the intermediate to high emission scenarios. So if we look at 2100 in the high emission scenario, without rapid ice sheet loss processes in 2100, we look at 2.6 to 4.3 feet as opposed to 2.2 to 3.8 feet. And then you can see also that increases the risk associated with potential rapid ice sheet loss, especially after 2100.
Got it. So we have a couple questions here from Ed Nieblock that I think you guys can handle. Is the Atlantic off New Jersey warming? How much is that contributing to sea level rise?
So I'll take that one. The Atlantic east of New Jersey, off the New Jersey coast, is warming. The effect on sea level rise, of course, is something that Bob talked about. This is the change in density of ocean water that happens as it warms. So when you warm the ocean, the same mass of water takes up more space, and that is one of the contributors to sea level rise.
Got it. And then another one related from Ed Nieblock is, have you included an AMOC slowdown in your scenarios?
Yeah, that's a great question, Ed. And the answer is it is only in there to the extent that it is in the coupled model intercomparison project projections that underlie our projections of ocean dynamic sea level. So there is not a scenario where we separate out AMOC collapse versus no AMOC collapse.
But that said,
That said, projections under suggest under from those CMIT models suggest that AMOC collapse is unlikely in the mission scenarios we're looking at in this century. But were it to collapse entirely, you would be talking about a couple of feet extra sea level rise.
and the current set of coupled model simulations do indicate some weakening of the AMOC over this period of time. So given that those models were used as drivers, that weakening is accounted for, but as Bob said, not broken out specifically.
Yeah, and I would say the historical, if we go back to our 1993 to 2021 budget, which Janine, I don't think you need to throw up the slide, but of the 5.5 inches total, about 0.8 of an inch of sea level rise over that period is associated with ocean and atmospheric dynamics. Some of that has to do with winds, but some of it might be reflecting changes in AMOC.
And I'll just interject here to say we have 3 minutes left. So Marjorie, I think we have time for one more question. So we'll rely on you to grab the last one.
Oh, well, so there's a couple of them. We might be able to get another one and we'll see. But have you seen, so one person is asking if you've seen a new paper by Barnes et al. 2024 that uses AI models and says 3 to 4 degrees C is possible by the end of the century. So I didn't know if anybody had a response to that.
I have not seen that paper.
I have not seen that paper either. Again, you could look at the difference between SSP 245, the intermediate, and SSP 37, the high, if you wanted to look at what the sea level implications were.
Okay, great.
And I know who the author is, and so I'll look for it, and next time I'll have a better answer.
Great. All right, Janine, one more or we're good?
If you can squeeze in one more, yes, go for it.
Okay. Okay, so would you say any of the statistics provided in the report sufficiently quantified the future likelihood of extreme events? Is this even possible for later years with unknown future changes to storms, VLM, and human development?
So I will answer that. The answer is we do not quantify the effects of extreme water levels on anything other than sea level rise, but both Tony and I are involved in a large collaborative project, the Megalopolitan Coastal Transformation Hub, which is a 13-institution consortium funded by the National Science Foundation and led out of Rutgers, that is doing work to look at changes in tropical cyclones and extratropical cyclones and interactions with decisions, including around things like land use and insurance that affect the associated risk.
Great, thank you. We good, Janine?
Yes, we are good. I'm glad we were able to get in that one more question. And so I will wrap up with some closing remarks. On behalf of all of us here at the New Jersey Climate Change Resource Center, we'd like to once again thank Professors Robert Kopp and Anthony Broccoli for today's presentation and all the members of the 2025 Science and Technical Advisory Panel, the report's peer reviewers, the review editors, the science and managing support team, the practitioners who provided input to the STAP deliberations, and the team at the NJDEP who supported this effort. A recording of this webinar will be available in the next day or so on the New Jersey Climate Change Resource Center website. And just a big thank you to all of you for attending this webinar and for asking your questions. We really appreciate it. And this concludes today's event. And thank you so much for your time.